first people trying to figure out how to do quantum things with gravity. I am, maybe you can say, one of the first people trying to do quantum information together with relativity and quantum field theory. There were some people before me, of course, but I was, I think, first wave of that. Okay, I made no assumptions or very few assumptions on background here. So apologies in advance for the boring parts for some of you that know very well relativity and know very well quantum theory. But hopefully you'll be entertained eventually. So let's see how far we get. Okay. Very basic. Here we have a space-time diagram. Time in the y-axis, position in the x-axis, right? So just getting familiar to it, this is how we move in space-time right now, right? Sitting there, if you assume that we are like in a way in a co-moving frame that is inertial. So this is how we're moving right now. We're moving in time towards the future. Nice. We can communicate. We can send signals from one another, right? That's how it works. I send a signal to you, a visual signal in this case, something at the speed of light. And of course, we can move. We can start running, or me going around, right? Move like that, slower than light. I cannot do this, though, for example. That would be moving faster than light. That's not allowed within special relativity, right? So far, so good. Everybody happy with all that. Now, changing reference frames. Changing reference frames is a little bit tricky when we consider relativity, right? You have here two different set of axes corresponding to two different inertial frames that have some relative speed with each other. This is taken very cheaply from Wikipedia, and I forgot to write the reference, so reference Wikipedia. Lorentz boosts, I think. And you can tell what happens to the axis. It's a hyperbolic, the plot is from Wikipedia. There's a hyperbolic rotation. So it's a rotation, if you want a rotation by an imaginary angle, if you want to be, I don't know, flourish about it. What it does to the axis, right, it tilts the axis like this, as you saw over there, right? That one reference frame and another, the time axis and the position axis are related to each other by this kind of hyperbolic rotation. So, for example, I have here 2 points in space-time, 2 balls in space-time. We call them events, right? Events are defined in a coordinate frame by the time coordinate and the position coordinate, and these two are what we call space-like separated. Space-like separated means that I can find a reference frame, I can do a change of reference frame in which the 2 events are simultaneous. You can tell these 2 events are not simultaneous in this frame that we have right now. They happen at different times, right? This is different time coordinate than this way, but I can do a hyperbolic rotation, a Lorentz boost, right? A change of inertial reference frame that make them simultaneous in this new set of new coordinate set. Great. We call those events space-like separated. And of course, you can tell already that 2 space-like separated events cannot be communicated by information transmission, no? Because information would have to travel faster than the speed of light to get from one to the other. Of course, we call time-like events. The definition is 2 events for which I can find a reference frame where the 2 events happen at the same position in different times. Now, you can tell these 2 are right now at different positions, right? The x-coordinate is different for both, but I can, again, do a Lorentz boost and put them both in the t-axis, right? So they happen exactly at the origin of the new frame. Make sense? We call that time-like separated. And if they're connected by transmission of light, we call them like-like or null separated. Probably very boring. You already know all that. This is the same thing again. Sorry about that. This shouldn't be the case. But just a little reminder that you can make animations in presentations. Sorry about this. All right. Now, relativity matters for quantum information, and I'm gonna try to convince you that it's actually important. All right, the notion of simultaneity, right? Now, you already probably know that the notion of simultaneity is relative. I have here 3 events, A, B, and C, right? And we're gonna look at them from the point of view of somebody at the position that B is, at the origin of axis here, of coordinates. And we're going to consider 3 observers actually at that position. One that goes with 0 speed relative to this axis, another one that goes with some speed towards the right, and another one that goes with some speed towards the left. And of course, you can see that in one frame, the 3 events are simultaneous, but in any other frame that is related by a Lorentz boost with the others, that gets some speed towards either the right or the left, the events are not simultaneous And in some frames, A happens before B and C, and in some frames, C happens before B and A. Does that make sense? Notion of simultaneity is relative, as I just said. All right, let's talk a little bit about a fun paradox. This is one that I always tell people. You're not allowed, okay, I'm going to do a little poll here. And if you know the paradox and know the solution already, good, but you're not allowed to play. This is for intuition-defined paradox, right? So please, I trust your good faith here. Don't play the game if you know the answer, okay? This is called the Bell Rocket paradox. So this is the universe where theoretical physicists live. So here we have two rockets. They are tied by a string, right, a rope. And this rope is very delicate, very fragile. It will break at the minimum amount of tension that you put on it, okay? Now the two rockets, because this is where we live, theoretical physicists, this is very nice. We have the two rockets have identical engines that will be switched on exactly at the same time from my perspective, and they will exert exactly the same acceleration, no deviations whatsoever. Everything's very idealized here, all right? The squares represent rockets. So they're going to lift off like that, all right? And the question I'm going to ask is whether the rope breaks or not. And before we actually answer the question, let's analyze a little bit the space-time diagram of this. Oh, there's also the y, but y's are so tough in physics, right? Anyway, let's look at that. So we have, excuse my hyperbolas. Those are not hyperbolas, but they should be hyperbolas. Look similar enough. So this is the trajectory of the two rockets. You can tell, right? Those rockets start with 0 speed. They would move vertically at some amount delta t that is small. But then, of course, start gaining velocity, right? So you start to move time-like moving diagonally in the diagram. And you see that eventually, at time infinity, they would touch the light cone, so the speed of light. Eventually, if you accelerate with constant acceleration, asymptotically, you will, in infinite time, reach the speed of light. Make sense? So they have the same engines, therefore the same proper acceleration for both of them. They would measure the same acceleration as they accelerate. And we can look at it from two different frames. Let's look at it from the frame that is moving with the launch pad, right? The frame that we see them. X is the height of the rockets. So at time 0, they're there. At time t1, of course, sometime after, they're at the same distance from each other, of course, identical. You've seen two identical rockets. They keep the same distance as they move, same engines. And later on, they're a bit, further away from the original position, higher in the sky, but still the same relative distance between them, as I see them. So I would conclude then, looking at that, perhaps, that the rope doesn't break. Because, the same distance between them, the rope doesn't exert any tension. So, yeah, the rope wouldn't break. Now we can take a look at the same experiment, but now described from a different frame. Let's put ourselves in the reference frame of one of the rockets. Remember the planes of simultaneity they're getting hyperbolically rotated, right? They're getting more and more closer to the half line that represents the light cone. So after some time t1, this would be the position of the rockets, the plane of simultaneity of the first rocket. These are all the events that happen at the same time for the first rocket. And then after some time after, like that. So when you look at it from the perspective of this accelerated frame, it looks like the rope will break. And they would tell you, the rope will break. Because the two rockets are getting further and further away as we advance time. Now, of course, the answer to that question, this is all classical. The answer to that question is either yes or no. There's no intermediate. Because, I once that I asked, somebody told me, oh, maybe both. Like, what do you mean both? If it might that I want to use the rope later. Like, can I use it or not? Oh, you ask me, no, but maybe no. So there's an answer to this question. Again, paradoxes in relativity are the names that we give to things that are not really paradoxes. Is that it may look paradoxical if we don't understand the problem fully, right? So let's do a little poll, like hands up. Let's count hands. Again, if you know the solution, you are not allowed to participate because it's spoiled, right? So, okay, how many people think the rope would break? Hands up. 1 person, 2 people, 3 people. You already said it, right? No. 3 people. 3 people or 4 with repetition. Oh yeah, nice. How many people think that the rope would not break? And this, again, keeps the trend. So we have, okay, let me just, hands up, hands up, hands up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. And this is great, 23. And this is great because this is a super interesting experiment, like doing this poll. Because when you ask an audience of non-physicists, the answer is what you would expect, 50-50. It's like that means the group knows nothing, has no information about it. When you ask an audience of physicists, the good thing about it is that you do know it, only that you express it wrong. Most people vote for the wrong option because the rope actually breaks. It does break, but it is deterministic. When you ask an audience of physicists that don't know, of course, the solution, without thinking of, I didn't let you think about it, so it's kind of unfair. But the intuitive answer that physicists give is wrong, whereas an audience doesn't know anything, so you or us, we are, as physicists, worse like a random monkey would do with an experiment like this. I guess we are all kind of random monkeys anyway, so fine. But it does break, right? So then the question is, okay, fine, you're telling me it breaks, but why? Why? Somehow the description from the inertial reference frame moving to the launchpad was more reasonable, I guess. The other one is weird. Well, it's very easy to explain from one point of view, and this allows us to distinguish the physics from the phenomenology, right? From the accelerated observer, it's very easy to explain, right? You could say, well, it's breaking because the other freaking rocket is going faster than us. It's accelerating at a higher rate, and therefore it's putting tension on the rope, and the rope breaks. Now, how would you explain it from the point of view of the inertial frame that is moving with the launchpad? Well, maybe if you've taken a relativity course, you realize that what we have here is an extended object, isn't it? What happens with an extended object that is going faster and faster from the point of view of an inertial frame? Aha. So the length between the rockets, right? If you want the length of the rope, if you want, will be contracted from my point of view. If I'm describing everything from the point of view of inertial, the length of the rope would be smaller than the original length. The 2 rockets will indeed remain at the same distance, but the rope is not as big as to cover the same distance as it accelerates. The rockets are putting tension on the rope, and the problem is that we assume that having constant distance is the same as having an extended object remain with the same distance. So let me just write, again, showing you that I can do very basic animations. Sorry about that. All right. And therefore, here we go. Again, it's not the Lorentz transformation that breaks anything. It's the tension that the rockets are putting in the rope. But that is a reflection that in relativity, you cannot have rigid solids, right? Like, there's no way to keep a rigid solid if it's moving relativistically. Does that make sense to everybody? So the rope breaks. And it's very unintuitive, as we proved here. All right. Cool. So there's these things in relativity that things are not like they feel they should often. Let's move to quantum a little bit. But let's keep in mind this. So everybody's familiar with Schrödinger cat, right? It's everybody knows like a live cat and sleepy cat, right? There was something weird with all that stuff, right? There's something that actually bothered people. And I have this because I'm going to compare popular science back in the day from popular science now. This was real from, it's blown up. It wasn't that big, right? But it was actually on the cover of the New York Times in 1936 when the EPR paper came out. And the media, Einstein was the first like global, worldwide, popular physicist without really doing anything for it. It was just what he did was so cool that people really, on the street, regular people, got interested in it. And this is about the EPR paper. And let's look at how popular science works. Okay. Einstein attacks quantum theory. Flashy headline. Okay, you can say maybe it's fair, maybe not. Einstein never quite liked some things about quantum theory. And then it says, scientist, which is Einstein, and 2 colleagues, maybe the people who prepare coffee for him, I don't know. So Podolsky and Rosen find that it's not complete, even though correct. Actually, that's accurate. Probably people don't understand it, they're reading that, but that's accurate. They say, believe a whole description of the physical reality, quote unquote, can be provided eventually. True for Einstein. Okay? So popular science in the 30s. What bothered Einstein a lot is the notion of quantum entanglement. So let's try to explain a little bit quantum entanglement. Again, apologies to those of you that know all this. It's important to explain it well because oftentimes in popular science, the notion of quantum entanglement gets sold as something really flashy that is not that flashy really in the way they put it. Let's distinguish quantum entanglement between versus classical correlations. Imagine that I have two balls, right? One white ball and a black ball, and I put them in a paper bag, and I can't see the inside. And I ask you, grab one. Grab one, but don't show me. Okay, and you grab one. And I say, okay, now go to Alpha Centauri to make it more sensational. Go to Alpha Centauri, and don't look at it. And then you're in Alpha Centauri now, 4 light years away. So I'm going to say, I'm going to measure the color of my ball. Measure. It's white, but not only that, the color of your ball is black. Isn't it impressive? And then you measure and it's black. And maybe I can tell you, I changed the color of the ball by measuring it. No, the ball was always black. But you see, the fact that I can guess the outcome of your measurement before looking at it is not the surprising part. Make sense? All right. Cannot make much money with that kind of trick. So, sure, if you pick one ball, you know that the color of the other one is correlated. Now, what makes it interesting or not intuitive from the classical point of view is that now I can have some probabilistic systems. By that I mean that the outcomes of measurements are not predetermined by the state of the system, but rather you can always give a probability distribution about the outcomes of the system. I put them in a bag, I get one, I throw the dice, I got dice in this case, I get a 10. Now classically, I have no clue what will be the result of the other throw, unless it's fair dice, right? So imagine, I have no idea. That gives me no information whatsoever about the outcome of a classical measurement on the other dice. However, if there were quantum dice, I could prepare states for which the outcome of the measurement on Alice would be correlated or even fully correlated with the outcome of the measurement that Bob makes. That is what is, let's say, special, if you want. It's a particular kind of correlations that even though the local measurements are not deterministically fixed, I don't know what the answer would be. It's random. If you think running a cat, I don't know if the cat would be alive or sleepy. I have no idea. But I know that if mine is alive, yours will be alive. So it's correlations between the probability distributions. Make sense? All right, now let's go to popular science nowadays. I have to say, I have nothing against Devin Powell. I don't know Devin Powell. I don't know who they are. But it was really nice because you Google is the first thing that you get. Let's read it. The race to prove spooky. Quantum connection may have a winner. You have your sensational headline. And now this is the more sensational thing. Entanglement breakthrough could lead to an unhackable internet. This is nice because you put together like buzzwords and then relate it to something that people know. This is 101 manipulation. Everybody is interested about the internet, on the internet, right? And then unhackable is kind of cool. Entanglement breakthrough, entanglement, ooh, nice. So you engage people. And then they say, particles don't obey the same rules as people. Good that they told us. Now, poke a particle and another one far away can instantly respond to touch without any messages passing through the space between, as if the two particles were one. Entanglement, double quote, is what quantum physics calls, I mean, this is when you take a quantum course, the second lesson, the intimate connection. Entanglement is what quantum physics calls the intimate connection. Everybody knows that that's what we use for it. Einstein called it spooky. To his dying day, he refused to believe that nature could be so unreasonable. There you go, something that's actually true. So popular science hasn't changed much from the 30s. It's become a little bit more buzzwordy in a way, but other than that, very similar. Now, the problem is that people think this notion, popular science notion of entanglement, that I make a measurement here and I'm affecting the system that is far away, is very popular. It's a very popular notion. And that notion is based on the notion, the Copenhagen notion of wave function collapse, which is a horrible notion. We know it's bad for many reasons. I'm not going to get into the many reasons, like self-consistency is a problem for it to begin with, but within quantum mechanics itself. But let's talk about what we just talked about. Let's talk about quantum entanglement in the context of relativity. So imagine that I'm doing the Alpha Centauri trick, and I'm measuring here. The person in Alpha Centauri is space-like separated from me right now. So the event where I measure and the event with the other, imagine that I'm Alice and the other person is Charles here, and they are measuring an entangled pair, maximally entangled state, maximally entangled qubit state, okay? And then somebody could say, all right, Alice measures a 1 or an alive cat, and the other person, now the state of the other person is being changed to be an alive cat. That suggestion of action at a distance is what bothered Einstein. Of course it's problematic. It's problematic because, okay, who measures first? Who collapsed the wave function here? Well, it depends who you ask. Different people will disagree on who measured first. It's intrinsically incompatible to think of wave function collapse in the quantum sense and the notion of relativity, in the notion of action at a distance that we're talking about. Does that make sense? Did Alice collapse the wave function? Was it Charles? Was it neither? What they measure simultaneously for some people? So we see that when we put relativity together with quantum theory, we may need to think a little bit more about how we explain, how we go about the whys, and how we go about the formalism. Now, relativistic quantum information, which is what I promised I would tell you what is here, is a field that is multidisciplinary. It's between quantum information theory, quantum field theory, and general relativity. Special and general, but a lot of general. So one side of it is, okay, can you actually use relativity to do things? This is the applied side, if you want. Can you actually do more things, taking into account that systems live in a world that is relativistic? Can you do more if you take that into account that you can do with just regular quantum information processing? It's similar spirit to quantum computing, right? Quantum computing is like, okay, quantum mechanics sucks, they said in the 70s. We are trying to integrate transistors, and when they get too close to each other, we have tunneling, and that adds noise. Quantum effects are the worst. Now, Feynman, by the end of it, and then many others after, said, well, what about quantum systems' power to actually solve problems? Maybe we can use quantum systems as a feature, and that's kind of the beginning of quantum information processing, right? The same way, relativity may actually unlock some things, or maybe tell you that you cannot do some, which is typically disappointing to some people. It's kind of fun, though. And sometimes it tells you how to do more that you couldn't do without doing relativity. The other side is to try to understand more about the nature of space-time and quantum theory together. How do we describe space-time in a way that is more similar to the way we describe everything else using quantum informational tools? Arguably, the second one is way more popular in the amount of results, but both have produced results and keep producing results. So if you have any questions, feel free to interrupt anytime. Very happy to. I don't want to lose anybody. I mean, I don't expect to lose many people with this yet, but I may. Let's talk about the measurement problem now. Examples where relativity can change things, the way we understand things. Okay. The measurement problem. The measurement problem, let me begin saying that in quantum mechanics, forget relativity, it's still very much an open problem. The problem of how you go, let me summarize the problem. Let me summarize the problem. Proposal. Let's see if some of my proposals, if they feel unreasonable, interrupt, please. Because I'm going to try to argue they're reasonable proposals. Proposal. At least some measurements can give values. If there are any experimentalists in the room, you may or may not agree with that, I don't know. But at least some of them may give values. Now, in quantum mechanics, those measurements, a measurement of a quantum system that gives a definite value, a definite answer, we model them with idealized measurements, projective measurements, the outcome of it, right? How to update the state after doing it, when it's non-destructive and you want to do more things on the system. Now, of course, more mathematically, idealized measurements, to simplify non-degenerate observables, update states through a rank 1 projector that is in the spectrum of the observable that you're measuring. Now, the problem is, okay, how do you go from a probability distribution to a number? In all the steps that an experimentalist takes from doing an experiment with a quantum system to writing down somewhere on a computer or a notepad the number 42 as a result, there are many steps that somehow transform or map a probability distribution and an experimental setting into a number. And that's what we don't quite have solved completely. We have a lot of insight in that problem. But that's where the problem lies. So it's non-trivial still within quantum mechanics. There's no relativity involved. Still, you can just not care, right? This is for foundations people. If you're doing experiments, really, I mean, it works. Why would I care? Let me do my projective measurement and not care anymore about it. Now, the question comes, okay, just a reminder that it's still an open problem. The question comes, what happened when you try to do the same with relativistic quantum mechanics, in particular with the right way of doing relativistic quantum mechanics, which is quantum field theory, okay? Little aside, there's something called relativistic quantum mechanics. Let me summarize a lot. I mean, I will have to qualify my statement very much, but let me just summarize saying, no, that's wrong. The right way is quantum field theory, okay? You need to do quantum field theory if you want to do quantum mechanics and relativity together, with an asterisk, but if you want more about the asterisk, you can ask later. Now, maybe we want to measure localized observables of a quantum field, like something that is not unreasonable. Imagine the electric field. I said in my room, but it could be here, the electric field here during the duration of my talk. So this is localized in space and time, right? And in fact, something you can measure. You can bring a sensor, and if you measure it, it's not unthinkable that you could get something of like 42 volts per meter. It's not unthinkable. Could be. It's about the order of magnitude that you would expect. Now, here's the question. Can you still not care about, well, as I formulate the question, it's not, but even if you do it right, you're going to get probably even poorer and less famous. But the point is, in any case, can you still get away with not caring about this in QFT? Summarizing a lot, the answer is not. 1992, we have Raphael Sorkin putting out this paper called Impossible Measurements in Quantum Fields. Now, let me just read the first sentence. It is shown that the attempt to extend the notion of ideal measurement to quantum field theory leads to a conflict with locality, because locality in the relativistic sense, meaning things that allow for retrocausality or faster than light signaling, things that are forbidden in a relativistic context. For most observables, the state vector reduction associated with an ideal measurement acts to transmit information faster than light. That's all that we need to read here. I can give you a couple of, a summary of the paper if you want. He does two things. It's a very simple paper. It's a really simple paper. First, he looks at something relativity aside. Okay, just to simplify what we're going to do, consider a two-qubit system, so two-level quantum systems. And I have one state, 0A, 0B. I perform a local unitary on A. I make an idealized measurement that projects onto the Bell basis. So that's a joint measurement of the two systems. Somebody does a Bell experiment and obtains that. And then 3, the expectation value of observables on B have now information about the unitary you acted on A. Now, question, surprise, most people knowing basic quantum mechanics would tell me, but no, you did something non-local when you measured in a Bell basis. That's something that is acting on both things, both systems at the same time, right? So the problem of signaling here comes from the non-locality of the measurement. And then he says, right, but when we go to quantum field theory, consider a state of the theory, and basically he argues, it's a long chain, that any projective measurement would be of that form on a slice of, done on a slice of space-time. It's actually really difficult to even formalize what it means to do a measurement in a relativistic theory, but it's done on a slice of space-time, and that means that the projective measurement is altering the field in a non-local region of space-time, and there's no way to do it. And this comes because there's a theorem that tells you that there's no such thing as finite rank projectors at all of observables of a quantum field in a finite region of space-time. I'm not getting into that, but that's the problem. Mathematically, in a rigorously formulated quantum field theory, the projectors, finite rank projectors associated to outcomes of an experiment that gives you an outcome, do not exist if they are localized. Now, the problem is the non-locality. Let me just tell you, this is a more modern take on the problem, and it shows that indeed you cannot do projective measurements in a localized region of space-time and get a value out of them. You cannot model with projective measurements any experiment on a QFT. If you care about relativity, if you don't care, it's probably fine. But if you care about relativity, if your experiment is trying to use relativity or measure something relativistic or see relativistic phenomenon, you cannot do that. You cannot model your measurements like that. We know we can do them in the lab, but you cannot model them that way. Does that make sense? Now, Sorkin said this concerning sentence, it is argued that this problem leaves the Hilbert space formulation of quantum field theory with no definite measurement theory. removing whatever advantages it may have seemed to possess. It's an attack on, it's actually a very good attack on the foundations of QFT. If you don't have a measurement theory, it's not a good theory. You need to actually be able to model how measuring the system alters the state of the system. So now what? Okay, I'm going to tell you my own take. There are two main, the measurement problem in QFT has been addressed in two different directions. One that I didn't include for time, but I have to give credit because these people are great. Chris Fuster at the University of York in the UK, the older York, right? The way they do it is they model detection. They model the act of measurement with an interaction with another quantum field. Formally impeccable, because of course it's all relativistic theories, and by construction the theory is relativistic. It's fine. The problem is connecting that to experiments or doing something that is complicated. You may know or may not know that bound systems in QFT are tough. So tough that we know how to solve one of them, and it's not very physical. But an atom from QFT, we don't know how to get. How does an atom appear from QFT? We know it's all fields, but how? It's just tough. I mean, we know. A theoretician will tell you, of course we know. Can you do it? No. But we know how, kind of, more or less. Anyway, so the problem is that the disadvantage that it has, the advantage is that it's impeccable. It's really a very rigorous way of addressing the measurement problem, and you can do things with it. The two weaknesses, if you want, is that difficult to connect with an experiment that you're actually doing. Second, difficult to actually apply to anything but free theories because it's tough. All right, let's go on my own take on this. I'm going to formulate some reasonable assumptions or proposals that I want from a measurement theory in QFT. If you don't think they're reasonable, please do tell me. But this is how we do physics, or at least theoretical physics. We start from some reasonable postulates, right? That come from informed by reality or by our observation of reality, and then we build the theory. And we can go crazy on the second part, but not on the first. We need to agree on the first. All right, I want it to be capable of producing definite values. That makes sense, no? There are experiments where you get definite values. Good. It needs to give me an update rule. That's the whole point. I need to know what happens with the state of the system after I've measured the system. I need an update rule after I make the measurement. I need it to be consistent with the theory. So if you're doing QFT, it needs to respect relativistic causality and also general covariance, which are the two features of a relativistic theory. And I would argue that it needs to be able to be connected to experiments. Otherwise, well, you're doing a nice measurement theory that you can put in a frame or something, but nobody will actually be interested in it. Maybe I'm being a bit unfair. People would be interested in it. You know, two ways are typically either you adapt the experiments to theory or you adapt the theory to experiments, right? So there's room in both sides. Is there an alternative to idealized measurements? Well, there are two main ones, I would say, or at least two that people are exploring, right? There are more, but those are the two that are more popular among the small sector of the world that looks into these things. One is what I told you by Fuster and Birch. I'm more on the line of what is called particle detector approach. So what does that mean? What's a particle detector? Now, the problem with a particle detector, first of all, we need to talk about what a particle is. And this is so non-trivial. How are you in terms of, I should give maybe some trigger warning about what I'm about to show you, because this is tough stuff. How much do you rely on the notion of particles in your life? If it's a lot, maybe you want to leave the room. I can give you 10 seconds. All right, so if you stay, be prepared. First of all, let's visit a paper by David Malaman, In Defense of Dogma. Let's just take the title. Why there cannot be a relativistic quantum mechanics of localizable particles. Now, I'm not going to get into the details of this paper because I'm going to get to another paper, but the title is very suggestive. It's telling you that there's some fundamental incompatibility, perhaps, between our notion of particles, our notion of relativity, and the notion that particles have to live somewhere, not in the whole universe forever, right? If you call particles plane waves, I'm fine with it. But they are very unphysical. They're not normalizable to begin with. Second of all, they live everywhere forever. And they always existed, and they will always exist. Does that make sense? Plane waves are not really very physical. No, when we talk about single photon detection, we mean in my lab, something generated a single photon and something clicked here. No? So it cannot be a plane wave. All right. You may know those, many people in quantum optics here? Yeah? You may recognize this name, right? One of the founders of the field, Nobel Prize in Physics, Willis Lab. In the 90s, he wrote this paper, and it's beautiful, the paper. It outraged the internet so much that sometimes you see posts on Stack Exchange, like, what does he mean? The paper is called Anti-Photon. And it's not about antiparticles related to photons, no. It's more literal interpretation of what the paper means. Let's read the abstract together in parts. It's really fun. Okay, it should be apparent from the title of this article that the author does not like the use of the word photon, which dates from 1926. In his view, there is no such thing as a photon. Only a comedy of errors and historical accidents led to its popularity among physicists and optical scientists. You see, when you win a Nobel Prize, you can do this stuff. Anyway, I admit that the word is short and convenient. Its use is also habit-forming. Similarly, one might find it convenient to speak of the ether or vacuum to stand for empty space, even if no such thing existed. There are very good substitute words for photon, e.g. radiation or light, and for photonics, e.g. quantum optics or quantum optics. Similar objections are possible to use of, I don't know why, of the word phonon, which dates from 1932. Now, this is the key. Electrons, neutrinos of finite rest mass, or helium atoms can, under suitable conditions, be considered to be particles. Key point, since their theories then have viable non-relativistic and non-quantum limits. There is a fundamental incompatibility to what we understand as physicists as particle. Maybe I should ask you what you think a particle, what a particle is, right? Because typically particle we associate with something that is kind of a small ball of some kind, something that is localizable in space and time, and there's only one unit of it, and it behaves as a particle. And what does that mean? Well, it behaves as, you know, it's contained, and I can talk about some distribution of position and momentum, maybe. Now, the problem is that states of relativistic fields, and that includes the electromagnetic fields, cannot be localized and be a Fock state of one, occupation number one, cannot be localized. Certainly, anything that you build in your lab is not going to be a photon. It may be close to it in the ways that you want it to be. I'm not saying it's bad. I'm just saying it's not a particle. It's something else. We may use the word photon, abusing it a little bit, but that's the thing. Like, again, particle, oftentimes you hear popular scientists say, oh, we have solar sails, and solar sails require, you know, because light is made of photons, they collide. No, electromagnetic waves transmit momentum. You don't need quantum theory for that. People understand sometimes quantum as discrete levels of something, and they say photons are the packets of energy of light. That makes no sense. No. Put a classical field in a Dirichlet cavity, there you go, discrete levels of energy. Put a free electron in free space. It's quantum, very quantum, continuum levels of energy. So it's not about being quantum now, even though the origin of the word comes from there, of course, but being quantum doesn't mean discrete anything. Being quantum is something different. Being quantum means that there's something called a quantization map, and then I go from a phase space that is classical to a Poisson bracket to a commutator now, somehow magically. Magically is actually important, but still. It's nice to be able to use this argument of authority here with Lamb, because it's one of the fathers of quantum optics. I have nothing against quantum optics. I love quantum optics. All right, let's move on. Oh, no, before we move, in that paper, it's kind of funny how he writes this paper. The summary of the paper said it's high time to give up the use of the word photon and of a bad concept which will shortly be a century old. Radiation does not consist of particles, and the classical, i.e. non-quantum limit of the quantum theory of radiation is described by Maxwell's equations for the electromagnetic fields, which do not involve particles. Talking about radiation in terms of particles is like, it's like using ubiquitous phrases as, you know, or, I mean, which are very much to be heard in some cultures. For a friend of Charlie Brown, it says, it might serve as a kind of security blanket. Now, I do use the word photon like everybody else, but keep in mind that from very foundational point of view, thinking of a photon as some particle of light of some kind, or a localized Fock occupation number one eigenstate that is localized, that's impossible. You cannot do that. It's not physical. All right? Good. So then what do I call particle detectors? Now, this is Unruh. This is William Unruh. Is I dare say the most famous theoretical physicist in Canada and one of the most famous in the world, for sure. William Unruh says particles are where particle detectors detect. So you have particle detectors, and what do we call particle detectors in theoretical physics or in QFT? Non-experimentalist. Particle detectors are non-relativistic quantum systems. What do I mean by non-relativistic? I mean a system for which a non-relativistic approximation is good enough to describe it. Think of an atom, right? If I'm doing a Stern-Gerlach experiment or some atomic physics of a hydrogen atom, nobody would expect me to do relativistic corrections to it. So it's a good enough approximation. And they can couple locally to a quantum field, like an atom does. An atom does couple to the quantum field locally. So atomic physics, or the interaction of light and matter, is a framework of particle detectors in this context. Now, are particle detectors good? Well, it certainly reproduces. We have many, many years of experience modeling the light-matter interaction to know that if you actually use atoms or atomic systems to interact with light, it does reproduce the experiment. The models that we have, after a lot of work, for sure, but it does reproduce experiments. Is it consistent with the theory? Well, that is the question that we addressed, me and my students started to address, which is, okay, you have a non-relativistic system interacting with a quantum field. It's non-relativistic. How can you guarantee that it's consistent with the theory? Are you going to do the same thing that the impossible measurements thing when you did a predictive measurement? So 2 things to check. I'm going to be very fast here, try not to get too technical, because I want to show you, how am I doing time-wise? How much time I have? Okay, perfect, yeah. So then I'm going to go relatively fast, but basically what you want to check is build atomic physics by construction, or the light-matter interaction. The models that people use in quantum optics are very much not generally covariant, very much not causal. So you may want to reformulate the models that you know in quantum optics to be generally covariant and causal. Some reference, I don't care. So you see this is, okay, here's a way of introducing. People working in quantum optics may recognize some things. This mu, you can put it as sigma x if you want. In that mu, there's an internal degree of freedom of the detector. And this phi is a field. Those of you working in quantum optics, maybe you do a single mode approximation or something, and that's one oscillator, right? It's very similar to James Cummins kind of model, only we don't do those approximations. No rotating wave, no single mode approximation, and I'm writing something, Hamiltonian density rather than a Hamiltonian. Because what is the Hamiltonian will depend on the observer. That's probably not surprising, right? Hamiltonian generates translation with respect to time, no? Okay, relativity, whose time? You cannot really define a Hamiltonian. So now in quantum optics, typically you do this. Free Hamiltonian for the atom, plus free Hamiltonian for the field, plus an interaction Hamiltonian, right? And you add them up. Well, you better, if you're adding them up, better they are in the same frame, like they're in translation with respect to the same time, but that's typically not the case. So you need to prescribe in a way that is covariant. There are some assumptions you have to make in the detector. For example, the detector has Fermi-Walker rigidity, meaning the detector has internal cohesion forces that when it moves on inertially are going to keep the atom together, things like that. All that said is basically the message is that yes, you can make it covariant. You can make it covariant, and you can also prove that there's no signaling. There are some things to be careful about, but basically tell you that the microcausality of the field with that kinds of prescriptions, it reproduces, all those models will have no value if it didn't reproduce atomic fields. They do when you take the non-relativistic limits of some of the approximations that are done. But it's formulated in a covariant, and you can put your quantum optics detectors in spacetime and start moving crazy and do dynamical Casimir under effect, black hole evaporation, these kind of things. All right? And they're okay. They're consistent with the theory. Not getting much into the details. Now, capable of producing definite values, and an update rule, that's non-trivial. Because with these models, what you do is you move the problem one level up, right? You're measuring a field. Instead of measuring the field, I'm coupling a detector. But now I have to measure that detector somehow and get a number, right? Let me just say it's non-trivial, but can be done. That means, okay, if I measure my detector and get a number, how is the state of the field updated? The state of the field updated, for those of you interested, would be updated by a POVM. And that POVM falls into the set of POVMs that are consistent with the theory. So again, take my word on it, I guess, because we don't have the time. This is where it's done. It can be done. So the message to convey is that with particle detectors, you can build a measurement theory for QFT that is based on the light-matter interaction, or inspired by the light-matter interaction. You can apply more generally than that. That allows you to do any localized model, allows you to model any localized measurement that you want in any space-time background that you want with any state of the field that you want in a way that is consistent with the theory, and you can use in regimes where the regular approximation of quantum optics falls short for, relativistic regimes, where relativity matters, I should say. Because you see, you know what the relativistic regimes is for light? All of them, because it's freaking light. Light will always move at the speed of light. So there's the issue is that what I mean is when relativistic phenomenology matters rather than, because it's certainly a relativistic system, whether people ignore that or not. Now let me give you one hopefully fun, very short result in RQI using this kind of stuff. Same as before, I'm going to give you some reasonable assumptions about wireless communication. This is an applied one, so let's see how that goes. Assumption 1, communication is mediated by real, and by that I mean energy carrying quanta, if you want. An emitter emits photons, you know, this is already Lamb would be cutting my head. An emitter emits photons, a receiver captures photons, right? In a way you can think wave packets, you know, carrying energy. Seems reasonable? That information is mediated, the communication mediated by real energy carrying wave packets? All right. Another one, information flow is carried by an average energy flow. That means that, by that I mean we cannot communicate without exchanging energy, right? Sending you energy. For example, I could tell you, okay, we're going to the movies. If you're coming, give me a call before 5. If you don't, I understand you don't come. Sure, if you don't come, you don't have to spend energy. But on average, if you do it every day, unless the answer is trivial and you never go, but nobody is that boring. So on average, you're going to have to spend energy. Make sense? From the informational point of view, you need to spend energy. Now, information reaches you when energy reaches you. Make sense? Reasonable? Okay. Another one, massless fields, right? Electromagnetic in particular. Communication is only possible, at least in vacuum, at the speed of light. Of course, not faster, but also not slower, because light, you don't slow it down in vacuum, right? So if you miss the beam, right? If somebody flashes, I thought there was a flashlight in my mind. So if you flash an empty seat, right? An empty chair, and then the light goes away, and somebody else comes the next day, they're not going to be able to get the message, no? Make sense? All right. So those are 4 seemingly reasonable assumptions. You know what? In general, none of them actually hold. And this is very surprising. Let's see why, and then let's do something fun with it. Oh yeah, this popular science again, but it was cool because we did apply to cosmology, and look at that. They did this nice hyped headlines with it. Of course, not really. Like, it will require years of work to actually do what they say we do, but you know, popular science. When it's nice to you, you have to take it. All right. So this is reliant on, even classically, you can understand. There are subtleties in the behavior of the solutions of certain PDEs, right? There's something called the strong Huygens principle. The strong Huygens principle states the green function of the massless wave equation in 3+1 d Minkowski space has support only on the light cone. Translation, any disturbances I do to the field propagate only at the speed of light. Nothing propagates time-like. It's only null signals, all the disturbances. Now, this doesn't hold in general, and it doesn't hold in curved spacetimes in general. And again, I'm not saying that in curved spacetime you can get secondary null rays or anything like that because space is curved. No, I'm telling you that you can have time-like signals with a massless field. You have an echo of the signal. Somebody can come later and sit on the chair that was flashed and the light went away and can get, in principle, get the message. And you can prove a protocol with atoms, with quantum emitters, where they read out this information. So let's just finish this. This is a result in relativistic quantum information. Let's just do a fun exercise. We can apply to cosmology, and in particular, let's do a fun exercise toy model. Imagine a cosmology that is like this. So you have right, you have your scale factor, and this is time, and then you get something like this. Right? So you get a universe that is contracting, and then reaches some critical regime. Imagine there is some quantum effects going on here, and there's a quantum bounce, and the thing starts expanding again. Make sense? That's an imagination thing. Huh? I'm not saying I advocate for the universe being like that or anything like that. So we know that at these levels of energy density, nothing bound will survive, right? Atoms are no longer there. People are definitely no longer there, but atoms, nuclei, they won't make it. This is too much energy density. Those things are not stable anymore. So they will not make it through a quantum bounds like this. Okay, this is we used actually a model from loop quantum cosmology, where they actually have a semi-classical solution. So this kind of thing can happen if the quantum effects are not that big. You see, it could happen that when you're in the quantum regime for gravity, there's not even a metric that you can talk about. There's something else. But you can do something called post-Einsteinian corrections to it, add quantum corrections to Einstein equations, and the same way we do post-Newtonian, when we add relativistic corrections to Newtonian gravitational physics. This is the same. You have a quantum bounds that is happening in a regime where quantum effects are small, still strong enough to trigger the bounds, but small enough that we can use a modified Einstein equation to model it. Okay? So we can do the full dynamics. This is done with the full dynamics. So imagine we live in a universe like that. Atoms, life forms, intelligence, bound systems like this will not survive a quantum bounds. Now imagine, so humans have been around for how long? If we are generous, 100,000 years, being very generous. And it's only very lately that we kind of started to understand this stuff. By this stuff, I mean the interaction of matter with quantum fields, cosmology, and these kinds of things, right? And we're still far from understanding it. Okay, let's imagine a species that is way more advanced than us. Imagine a species that existed way in the far past for trillions and trillions of years, right? Extremely advanced, they crack physics completely. We don't know what they would look like. It's a level 3 intergalactic civilization or even more, but that's the best model we can have right now with what we know. So imagine we have this ancient pre-bound civilization. And they know that they're headed for a quantum bounds. And that means that they know they will die. They will not make it. Nothing they built, nothing of their legacy will make it through something like this. It's too bad. So what would they do if they wanted their legacy to survive? So this is a real published exercise, if you want. But one thing that they can do is they can encode the information about their legacy in quantum fields. And they can get atoms, right? They can use those atoms to encode information into the quantum field interacting with it. The fields will be there. They will just be in a region of strong interaction, but the fields will still be there. So the question is, okay, if they encode the information in the quantum field, and then you go through a quantum bounds, assuming optimality. So the assumption here is that these people think that in the future there would be a civilization at least as advanced as they are, that would be able to know that if somebody existed before would have used the optimal encoding, of course, and know how to decode that optimal encoding, assuming that. How much information is recoverable nowadays? And the answer is that information that is encoded in this time-like echo, it's fully recoverable, assuming that you can cover a good swath of the time-like envelope of the phenomenon where you encode it. Now, what's going on, what is behind this, is that in quantum theory, you know that in quantum theory you cannot destroy information or create it. It's unitarity. You familiar with the Church of the Larger Hilbert Space? Yeah, I'm a member. So the Church of the Larger Hilbert Space basically tells you, if everything I'm a member, you know. If we assume that quantum theory explains everything, which is far from being known, of course, we have pesky gravity, which we don't know. We hope so, but, right? But if we have a universe, and you can dilate your system as much to include everything that you can think of and call that universe, if quantum mechanics is right, evolution has to be unitary. Unitary evolution cannot destroy information. All that it can do is scramble it. And there's a lot of super nice thermodynamics that I'm not going to talk about associated with the scrambling of information. But this is what you do. Like, you say, you've destroyed the information doing that, no shredding paper. Not really. Somebody with enough patience, I mean, have you seen Better Call Saul? They do that, actually. They get all the pieces of paper, they put them together, and they read the documents because the information is still there. It's just scrambled. They make it really difficult to put it back together, but that's all. They don't destroy it. So you can have something like that again. This is just for effect. Huh? So maybe we look at the echoes from the early universe, and maybe we can decode something like that, right? And that's what's behind these things. Anyway, what I wanted to tell you, I'm not going to get obviously into the technical details, but what I want to tell you is that relativistic quantum information looks at these kinds of things, both from the fun point of view, I hope that was a fun example, and from the applying point of view. There are phenomena like entanglement harvesting, which is the ground state of quantum fields contains entanglement. The vacuum is entangled in different regions of spacetime. You can harvest that entanglement. You can use that entanglement. You can decode aspects of the interaction of theory, of your theories with gravity, looking at that entanglement structure and so on. But this is more or less what we do in relativistic quantum information. We also kind of try to generalize the models using quantum optics. I think generalize is the right way because we don't start from them. It's going from quantum fields in curved spacetime and doing the same steps that people like Lamb and others, like Miloni, well, all the founding fathers of quantum optics did, from quantum field theory to quantum optics, but in the context of QFT in curved spacetimes, and keeping in mind that we don't want to spoil causality and general covariance, and then see all plethora of new phenomena when you have curved spacetimes, and see if we can learn anything about quantum gravity with that. And I think that's probably fine in terms of time. Yeah. Okay, so I'm going to leave it there, and any questions, please do ask. Yeah.